simulation all around Europe at EngineSoft. And I'm very excited for today's webinar. We are here with the Dallara team presenting their work on digital modeling of fuel sloshing in advanced motorsport. So today with us, we have Massimo Stellato.
Good morning.
Head of Vehicle System Engineering at Dallara, and Giuseppe Usai.
Good morning, everyone.
Project engineer in the same group. So I will quickly leave them the floor so they can discuss their agenda, the agenda of their presentation, and their work. And I really think that the results they will showcase really shine in showcasing how meshless simulation with Particleworks can benefit in R&D. Okay, so we will disable, I think, our video, and we will share the presentation now.
Thank you. So thank you, Michele, for the introduction. So today we speak about the sloshing simulation that we perform with Particleworks, in particular for motorsport application. This activity is performed inside our department in Dallara, which is the Vehicle Systems Department. Okay, now just I share my screen. Okay. I provide you just a short outline about what we will discuss. So we will speak shortly about Dallara overview. After that, Michele will speak about Particleworks, and in the last part, Giuseppe will go in detail about the sloshing activity. So, Dallara, some words about Dallara. We are a community that invests every day in a sustainable way for a better future and gives support, security, and solidarity to its people, family, and its territory with appreciation and gratitude. Our mission is to design and produce the fastest and safest cars in the world. We are around, currently we are 750 employees. We export outside the Italy more than 9% of our product and service. If we see our sales by business unit, we are involved, as you know, mainly in the racing, 72%, an important part in the automotive field, 25%, but also is growing the part relative to aerospace and defense. Currently is 3%. Typically, so our business model are production for customers, 24%, engineering customer, 28%, and engineering production of Dallara brand, 48%. We have many buildings in the world. Our headquarters is in Varano de Meregali, very close to Parma, with our headquarters is dedicated for both engineering and manufacturing. Always in Varano, we have the Fabbrica Dallara, where we produce the Dallara Stradale, which is the only road model branded Dallara. So this is dedicated to the manufacturing. Always in Varano, we have the Dallara Academy, where we have a museum and also a university course about engineering, where both professor and engineer teach in this course. In other town close to Parma, called Collecchio, we have Dallara Compositi, dedicated to manufacture the all the carbon fiber product, And Dallara USA, we have another facility dedicated to American market. Here you can see the main milestone about Dallara that has been founded in 1972. The first model was a race car, a three-seater race car. In 1978, the first Formula 3 chassis, and the next year we will have the next Formula 3 car. So we have always from the beginning worked in this championship. In 1984, the first wind tunnel. After we produced the first carbon fiber chassis, we started to work in 1988 in Formula One, and in 1998 in IndyCar. In 2000, we developed the first Veyron for Bugatti, which is a very important customer for us. In 2011, we developed our driving simulator. In 2012, we opened the facility in Dallara, USA. After that, we started with Dark and Dallara Composite, and in 2017 we produced the Dallara Stradale. In the next year, we opened also Dallara Academy, and we produced the Dallara Experience, which is the track version of Dallara Stradale. Here you can see the main business unit, which are racing, automotive, and aerospace. And for each one, we provide engineering consultancy. We are involved with prototype and series production, service, and also race and worldwide spare parts support. And here you can see our main competence, which are lightweight design and structural optimization. We work massively with simulation in holistic way, so with all perimeters typically together, vehicle dynamics, passive and active cooling system, but also ICE and electric powertrain. Another competence is aerodynamic, electronic architecture and development, production and assembly, and also indoor and full vehicle outdoor testing. We have dedicated test bench, cooling rig, chassis rig, and poster rig, but we follow also the track validation of our car. Here you can see our main approach is very important for us. The first step, which is the research, where we involve massively our resource, design and simulation. After that, prototype validation, and at the end, a series production. There is a continuous interaction between all these steps, in particular between the research and the prototype and validation. Here you can see our many product or many car, not all because many projects are confidential. Here are reported the project that which are public. And at the end of this last part, these are the activity that we perform inside the vehicle systems engineering department. In particular, we deal with the calculation and simulation about cooling system to size and define the layout of ICE, electric, and hybrid vehicles. We perform holistic simulation with vehicle dynamics and systems together. The sloshing simulation, which is the topic that we speak today. Also HVAC system sizing and cabin comfort optimization and brake cooling analysis. Further that, we are involved also with the testing. Indoor testing, we have a dedicated cooling test rig, where we measure and validate all our heat exchanger, but also we follow all the system validation during the track test. At the end, we're involved also in academic and research activity. So we teach it. We have at Mooner a complete course about the cooling system. Now for this first part, just about Dallara, I finished, and I leave to speech Michele.
Perfect.
Thank you.
Thank you, Massimo, for your kind introduction. And just please confirm that you can see my screen.
Yes, we can see.
Okay, perfect. So I will just take on briefly introducing the methodology, the fluid dynamics methodology that will be used and that was used by Dallara team. And it's based on Particleworks. So Particleworks is a meshless CFD, computational fluid dynamics tool that is widely used in the automotive sector. The method is a meshless approach based on the moving particle simulation. So it basically solves all the traditional CFD equations, but with a Lagrangian type of approach. So basically the fluid is discretized automatically by the software in particles, and those particles are tracked during the solution. So we can see here that whenever we have a system with complex geometries, splashing and sloshing or acceleration that will cause, of course, the fluid to move around in a gearbox or in a tank. So for this kind of system, really this method, as compared to conventional CFD, mesh-based CFD, can really show advantages. So in fact, we can see that the pre-processing steps are much shorter. Usually we can directly work with the geometry as complex as we would like. And the hardware time, the simulation time is actually way shorter whenever we are dealing with the flows that I mentioned. So splashing phenomena, sloshing, and so on. So for this kind of application, as compared to mesh-based CFD, we are looking into hours, or let's say 1 day of simulation instead of weeks. So in general, the features, as I mentioned, are that we don't need to prepare the CAD for simulation in this method, so we can directly import it, and that was done with the Dallara fuel tanks. It's very simple to model the fluid dynamics, so we don't need to have CFD experts or let's say engineers specialized in numerical modeling for this kind of system and application. And we can also leverage GPU computing, so graphic card computing, to speed up the solution actually of our simulation, because the methodology itself can be parallelized very efficiently. So showcasing a little bit of the features of the software that will be discussed, one important feature that was integrated in the sloshing simulation is the ability in Particleworks to discretize solid elements with particles. So we are not only dealing with the fluid and the fuel, but as you can see in this example, we can handle solid material. In this example are screws floating and experiencing the fluid forces. But in the example that will be discussed are Teflon spheres integrated in the tank and interacting with the fluid. So this is another feature that is very interesting and that was used by Dallara to improve their design. So effectively, you can build a fluid structure interaction between, again, the fluid phase and the solid phase in one digital interface, in one digital solution that is Particleworks. Also, recently, the software included the possibility to have high-resolution regions. This is a very exciting feature because, as you can see, we can now define, and in sloshing simulation, it can be very beneficial. We can define areas of the domain where the fluid particles are smaller. So let's say we have a sump or a pump region that we want to discretize, or the surrounding of the pump, we want to discretize in a finer way. We can easily build a high-resolution region around that, and we can solve elsewhere with a bigger particle size. So effectively, we improve our computational time instead of having to solve for all the fluid domain with the very small particle size needed to capture the flow near the pump. With Particleworks, we can define regions boxes, or actually we can import files defining the custom shaped region we want to have for this kind of high resolution area. Here is an example in vehicle, external vehicle contamination and interaction. So we have some weighting of a big truck with a lot of cars on top of it. And as you can see, maybe you can appreciate that farther away from the truck, we have bigger particles that are redefined and meshed with a smaller feature very close by to the truck. So in this way, we have better splashing phenomena very close to the bodies, but then we don't where we don't need high resolution, we just keep the particles a little bit bigger. And here is another example for a weighting type of application. Basically, we want to analyze the amount of water that could be intaken by the car body, and that could enter the cooling system, for instance, from the front of the car. And as you can see here, we could have very small gaps that should or would maybe need a particle size of 5 millimeter, in the range of 5 millimeter. But if we discretize all the fluid domain with that particle size, we are looking into 8 hours of simulation time for the entire simulation. If we take advantage of the multi-resolution approach, you can see here the box. Actually, we can define 5 millimeter only inside the box, and overall, we are reducing the simulation time by a factor of 2 or more. And at the same time, we guarantee that the higher resolution is present in the desired area. In terms of physics, we, of course, don't only simulate water or Newtonian fluids. We can integrate snow, mud, with different type of modeling, also rain simulation. And as you can see, actually, what you see here is an air field, transient air field, computed, again, inside Particleworks. So the software can handle fluids, but also air simulation, coupled or let's say solved beforehand, before the fluid flow. But effectively, we can see that we can integrate different physics, different phenomena in one workspace, thanks to that. So this was it on the features. Again, I focused on vehicle application. Of course, there are many other applications in terms of transmission, bearings, lubrication, e-motor cooling, or other fields that are not related with the automotive sector. But since today we are talking about vehicles and motorsport application, I just wanted to have an overview of the application in this direction. So now I will stop sharing my screen and I will give the floor to Giuseppe for the main results.
Very good.
Okay.
You can hide maybe the bottom. At the
Yes.
bottom.
So,
yeah, perfect. Thank you.
Yeah. Okay. Sorry for the inconvenience. Sometimes it happens. So I was saying I wanted to have a small motivation to explain to you why we need such tools in our products. Of course, the first point of interest is to improve the design. That means, in our case, to limit the fuel center of gravity movement, and also to maximize the pump efficiency. This is mainly a problem of reliability for the whole car, because of course the fuel needs to go to the engine. We don't want any engine cut off at any point in the race, even when only few liters are left in the tank and the car is about to go in the pit stop. And the second point is to reduce simulation runtime and pre-process complexity. In fact, as I will discuss later, we used to perform such simulations with traditional CFD tools, so that use the common finite volume methods. But then we decided, with the support of Particleworks, to test the software and to see if we can actually have an advantage on the track. So why we need such simulations? Everyone knows that a lighter car is a faster car, but on point of that, if we have a light car and we have a lower COG, the car will be even faster. So it is important to study how the center of gravity of the car will evolve around a lap. And of course, we have the two contributions: the center of gravity of the car itself, of the chassis itself, and then the one, let's say, of the driver and of the fuel. So excluding changes to the architecture and general shape of the car, our goal as manufacturers is to put the driver and the fuel as close as possible to the ground. And by that, I mean that if I'm designing a GT car, I can't have the driver seated as in a formula position, and we have to follow also a lot of constraints given to us by the organization that is often the FIA. So on top of these constraints, we try to limit the fuel sloshing and to have the driver seated as low as possible. It is also important, as I mentioned before, to know if the feed pumps operate at high efficiency to avoid, of course, any issues during the race. This is a portion of one of the simulations that we performed. On the right, you can see the acceleration profiles. In blue, the vertical acceleration, that is this direction. You can also see the axis on the bottom left. On with the red, the x directions, that is normal to the screen surface, let's say, and then the y direction, that is the lateral direction. So in this small segment, we see a portion of accelerations in which the car is first in a, let's say, stable condition with almost constant lateral and longitudinal accelerations, and then we have a rather strong transition with heavy braking and then acceleration and then also cornering, first to the left and then to the right. And we can appreciate here the result that we obtain through Particleworks. So now, going more in detail on the boundary conditions. First, we performed a particle size sensitivity study that was performed with, let's say, the same boundary conditions apart from the particle size. Here on the right, we see the 4 simulations that we performed at the start, and the only difference between them is the particle size. And as a consequence, also the time step changes, because that's directly related to the particle size. So as the particle size increases, you can see that also the time step increases. And this, of course, translates in a lower number of particles, but also, and at the end, a lower simulation time. On the left instead, we can see the inputs and outputs of the process, let's say. Of course, we have as an input a geometry that is an STL file of the whole tank, with also all the components modeled inside. We, of course, need the fuel properties. That means fuel density, viscosity, and surface tension. That's really important. The acceleration profiles that I will briefly discuss in the next slide. And then, of course, we need to set some solver settings, such as how we want to solve a pressure and viscosity, explicit or implicit solvers, the time step, the particle size, but also the interval on which the software saves the results, so that we can visualize and analyze and some others. And at the end, we get the XYZ center of gravity position and the pump's flow rate. So a bit of deep dive into the acceleration profiles. So we set up a 35 second simulation in which the accelerations are varying with time, of course. And this in particular is not a full lap, but is a combination of corners that are deemed representative of the sloshing problems, of the sloshing problem. This means that maybe a lap is 1 minute and a half, but maybe I spend a lot of time in a straight where basically nothing happens. The car is accelerating in a straight line, no lateral accelerations, and after I am out of the corners, of course, the longitudinal acceleration is not enormous, so there's actually no need to spend resources in simulating a condition that is most likely not a problem for the car. So we selected some corners. Here we can see in blue the lateral acceleration, so we can see some very demanding corners with fast left and right change of directions, together with acceleration and the braking phases. So now finally to the results. These are the results of the particle size sensitivity study, in which the goal again is to define and find a particle size that allow us to study a wide variety of solutions in a brief time, but at the same time not without any major issues, let's say, in terms of accuracy. So we want, of course, smaller simulation times, but also good accuracy results, because we are engineers, of course, and everyone likes that. So regarding the X and Y CRG positions, we basically see a negligible differences between the curves. They're basically all overlapped, one on top of the other. So in this case, we can't really say which is the best, and if one solution is better than the other. When we go instead to the Z CRG position and to the runtime, we clearly see an advantage. In particular, when we go to the Z CRG position, we see a maximum error of 0.9%, when we increase the particle size from 2.5 to 3 millimeters, and that error increases to 1% and 2% if we keep increasing the particle size to 3.5 and 4 millimeters. The differences here are noticeable, especially in this region, where we see that especially the 4 and the 3.5 millimeter curves, that are the red and the green ones respectively, differ from the 2.5 millimeters. The differences are basically carried in also other parts of the simulation, such as, for example, this last one here, or this transient, this, let's say, particular section here. And talking about runtime and the comparison with CFD, we had this experience on this kind of simulations with traditional CFD, as I mentioned before, and in that case the runtime was around 24 hours. Here on the left, we don't see the CFD curve, but it was well aligned with the 2.5 millimeters, and for sake of clarity, we chose to not display that curve in this plot. But when instead we go to Particleworks, we see a runtime with the 2.5 millimeter solution of a little bit more than 10 hours. It was around 11 hours. I repeat, with results that are very close to the safety ones. And then as we keep increasing, the particle size towards 4 millimeters, we see a strong reduction in runtime due to the fact that, of course, we have a smaller number of particles. We go from 3.2 millions of the 2.5 millimeter solution to around 0.7 millions for 4 millimeters. And on top of that, as the particle size increases, also the time step of the solver increases. So, of course, to perform a fixed length of this 35-second simulation, we need less time. And that's really an advantage, because you can understand that if I can run a simulation, for example, in 3 hours, that means that I run like 7 times the simulation that I would run with a traditional CFD in the same time frame. Finally, for the pump flow rate, here I reported only one plot, because we have actually 6 of them on the bottom of the tank. Here we see like a bigger discrepancy compared to the center of gravity positions, and in particular here we see the limit of a bigger particle size, and in particular the 4 millimeters simulation that is not able to replicate at all what instead is predicted by the 2.5 or 3 millimeter simulations that are the closest to the expected, let's say, result. So at the end, we can say that we chose to set up our simulations on a particle size of 3.5 millimeters, and therefore all subsequent simulations have been performed with that particle size. This was just the first study that we performed with the support of Particleworks in order to find the best trade-off between computational time and accuracy. And then we performed other kind of analysis. One of them is showed in the next slides. So, of course, when with the goal of optimizing the center of gravity position over a lap and to optimize the fuel pump efficiency, one can think of different solutions that may involve the change of the actual geometry of the tank or of the surfaces and of the components that are placed inside it. But we decided like to study a particular yes, a particular, let's say, solution that involves the use of Teflon spheres inside the tank in order to avoid, of course, the fuel sloshing. So in this case, we set up some, I think, around 30 Teflon spheres inside the tank, and of course we assign to them the given properties, so basically the density, and then the software automatically, let's say, evaluates the interaction between the fluid particles of the fuel and the Teflon spheres. The Teflon spheres that are in this case modeled with are discretized with particles with the same particle size of the fluid. So it means that when we look at this sphere of a diameter of 70 or 100 millimeters, that sphere is basically made of particles with a particle size of 3.5 millimeters. This has the main advantage, let's be honest, that no additional license is needed, because Granuleworks would allow instead to have only, let's say, one body as a sphere. Instead, in this case, we have a lot of particles that are, let's say, glued together to form the Teflon sphere. So now to the results. Here we are comparing two simulations, one in which we have only the fuel, and another one in which we have a fuel and these Teflon spheres. In the X direction, we see a reduction of the COG movement of around 14%, while no significant changes in terms of fuel flow rate were noticed on the fuel pumps. When we go to the Z and Y directions, we see a interesting result, mainly because in the Y direction we see, for example, that the spheres help in both left turns and right turns, because we see that the center of gravity tends to stay more around the center, and of course it does not deviate so much from that solution. And also in the Z direction, where we see a 17% lower COG of the fuel compared to the condition in which we do not have any fuel fuel or any Teflon spheres inside. So the solution is actually quite interesting. Of course, there are other topics of that need to be analyzed if it is decided to put this solution in the car, but it is interesting to see that this kind of approach is possible to be analyzed with Particleworks. So we are now at the conclusions, and at the end, as I just said, we can say that the moving particle simulation technology allowed us to study effectively what we wanted to see. So we wanted to analyze the center of gravity variation during a transient maneuver of a race car, and also to study the pump efficiency. And therefore, we have verified, let's say, that the software will allow us in the future to analyze different kind of solutions, finding hopefully the best one that works in the racetrack. So I I tried to be as concise, but also as let's say complete as possible. So from my side is all. If you have any
Perfect.
questions, me and Massimo are here.
Perfect. Like sharp on time, I would say. Thanks again, Massimo and Giuseppe, for your very interesting presentation. So we have quite a few questions. I will read them and you can answer if possible.
Yes.
One question is about the type of simulation. Was it a multi-phase or single phase with only fuel?
It was a single phase simulation with only fuel.
Yes. So, and then we introduced the solid with Teflon, but air was not included. Yes.
Air was not a part of
Yeah.
the simulation.
Then there is a question, again, if you can answer, about the range of acceleration used as input in the simulation.
I can't really share that information.
Okay.
I mean, it's let's say it's a race car, so we're not talking about 1G that my Toyota Yaris can perform when I go home. So we're talking about few Gs, but
Okay.
yeah,
Yeah, I think
few
that
Gs, let's
answer.
say.
Yeah.
We can tell which is a real data acquisition, so
Yes,
relative
exactly.
to acceleration of profile that come from real data acquisition of a race car.
Perfect. Thank you. And were there any comparison with testing? And if yes, do you have comments on that?
For the moment, no. We validated it through our CFD model, which is a consolidated method. As next step, we will plan for sure also to have a comparison with the test, but we have to think the right test because it's not easy.
Yeah.
Thank you. So the other question is about the spheres, the Teflon spheres. What would be the impact from initial amount of fuel? So I don't know if I understood the question.
So you basically are asking if if I have like that tank full at 80% versus 20%, what's the impact on the results in that regard? At the time, we did not perform such simulations. Also, mainly because we were interested in a sort of intermediate condition. So the tank should have not been completely full nor completely empty. Let's say a condition where you are half of the stint more or less, with the tank that is around 50 or a little bit more percent. So we actually don't have a comparison to in this regard to different fuel levels.
Yeah.
In this simulation.
So then we have a question about turbulence model. Was it used?
Inside the software, I'd say no. In this case, it was not used.
Yes, indeed, it was not used for this kind of application, and yeah, it can be handled, but for this kind of application, we don't usually enable it. And the influence of this model was not monitored. Yes. And what GPU card was used?
It was used a single NVIDIA A40.
Okay.
So all the simulations, all the simulation runtimes that I showed when we talk about Particleworks are for a single A40 GPU.
Yeah. Perfect. So we can also do multi-GPU, of course, and scale on bigger hardwares. So a lot of questions coming in. I will try to address all of them. Okay. There was a question about the comparison with standard CFD results and if they were similar. I think you briefly mentioned, but if you
yes, they were almost identical. So when we decided to perform the study, of course, to see, okay, let's see if we can decrease the time needed for each simulation, keeping the same accuracy. That was the approach for the study.
The approach is we found the sites, the particle sites which match the CFD, and from that we analyze what is the time difference and what is the different accuracy increasing the sites.
Perfect. Thank you. So one question about the Teflon handling, maybe I can also answer that. So indeed, there are two possibilities for the solid. One is the powder with Granuleworks module that, as mentioned, would require an additional license for Granuleworks. That the advantage there is that you can define, let's say, a distribution of dimensionality of the, let's say, spheres that is custom made. So it will be a little bit easier to set up the Teflon phase at the beginning of the simulation, while if we work with the solid discretized with particles, as we did, we needed to import separate spheres and initialize them with particles connected with that solid Teflon element. So it's a little bit longer, the setup, but yeah, at the end, you can achieve the same results and keep only one solution, so only Particleworks solution. I hope I answer. Since it was a little bit more on the software, I took on that. Okay, so again, if you have other comments or curiosities, please let us know. Otherwise, I will just thank you all for joining today's webinar, and thanks again to Massimo and Giuseppe and the Dallara team for the opportunity to showcase this real-life example of using simulation to improve and to make faster cars, actually. So it was really a pleasure to have you here. And again, thanks, Massimo, thanks, Giuseppe.
Thank you.
Thank you, Michele.
Yeah.
And thank you to you for this opportunity.
So until the next time with perhaps the, let's say, on-track validation of the methodology. Looking forward for that.
Sure.
Yeah.
Sure.
Bye, everyone. Thank you.
Goodbye. Thank you.
Bye, everyone.
Bye-bye.
Bye-bye.